In today's video, we're going to do a quick overview of a new factoring strategy that we're going to add to your list of types of polynomials that we can factor. So we already have greatest common factor, simple trinomials, hard trinomials, perfect square trinomials, and difference of squares. We are now going to add to that list something called sum and difference of cubes. As it says, it's a pattern that holds true for when you have two perfect cubes either added. So unlike squares where you only have difference of squares, this pattern also works for sum of cubes. So it's sum of cubes and difference of cubes. Now the pattern is a little bit different than difference of squares, so don't say, oh, well, it's just the same thing, because it's not. If you have a to the third plus b to the third, that would be the sum of two perfect cubes. Now when you look at the pattern, the way it works is, so if I had an a to the third and now I have a, that means I took the cube root of a. So it's the cube root of the first term. If it's a plus, it's plus the cube root of the second term. All right, so that's easy to get the first factor. So that's how you generate the first factor. You take the cube root of the first term. If it's a plus, it'll be plus. Then you take the cube root of the second term. Now, the second trinomial here, that's your other factor, it's created looking at this one. After you get this first factor, you square the first term, so a squared is that. You multiply these two together and reverse the sign. So notice how this is a plus. This will always be the opposite. A times b would be ab, and then a negative in front of it. Now don't confuse it with the three-step rule for squaring a binomial where you multiply and double. You're not doubling. You are just multiplying and reversing the sign. And then you square this one. That's always going to be positive because it's created by being squared. All right, so it is cube root of the first plus cube root of the second. And then to get this second factor, you square this one, product of these two, reverse the sign, square this last one. It's the same pattern for difference of cubes, except of course it's cube root of the first, same sign, so cube root of the second. Now to create this, you square the first, product of these two, reverse the sign, square the last one. That is called sum and difference of cubes. Now I'm just going to do a few quick examples of this. I'm going to do these by hand here. If I go, let's go start out easy. Let's say I had x to the third plus 8. So you got to be familiar with some of your perfect squares. So 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is maybe 216, I think. Anyway, it's usually one of those obvious ones that you should know off the top of your head. If I get into this one and I notice I've got a perfect cube plus a perfect cube, I now know that I can factor this. And I can factor it by taking the cube root of the first, sine of the middle, cube root of this one. Now square this one. Product of these two, which would be 2x, reverse the sign, and then square this one. Good news is this factor here, the trinomial, unless you missed a GCF or something up in the top, it will never have anything other than a greatest common factor in it. Just because of the way you create it, it'll always be non-factorable. All right, let's look at another one. Let's suppose I had 27y cubed plus 125 z to the, let's go 6. So in order for an exponent on a variable to be a perfect cube, you need to be able to take a third of it, because cube root means divide your exponent by a third. It's the exponent 1/3, right? If I have x to the third and I wanted to take the cube root of it, what that means is x to the third raised to the 1/3. Multiply the exponents, that's why you get x to the 1 when you take the cube root of something. It's a bad 3, sorry, that's cube root. All right, off we go then. Let's follow the pattern. Cube root of this one. So the cube root of 27 is 3. The cube root of y to the exponent 3 is y. If it's a plus, it's a plus. Cube root of 125 is 5. The cube root, meaning divide your exponent by 3, of z to the 6th would be z squared. Square the first, 9y squared. Don't forget to square the number in front and the variable. Find the product of these two, which would be 15yz squared. Reverse the sign. Minus 15yz squared. Square the last one. Plus 25z to the 4th. Square the numerical coefficient and also square the variable. And again, this will not factor any further. Let's go, I don't know, let's go 125 a to the 9th minus b to the 12th. So this time it's difference of cubes. And again, the giveaway here are the exponents being divisible by 3, that they're perfect cubes, and 125 being a perfect cube that I recognize. So I say, oh, this is the pattern of difference of two cubes. Cube root of the first, 5, a to the 3rd. Divide that exponent by 3, it'll become b to the 4th. Square this one, 25a to the 6th. Product of these two, and switch the sign. 5a to the 3rd, b to the 4th. Square the last one. So when you square, you double your exponent. There you have it. Let me try another one here. Let's go 64 x to the 12 minus let's go minus 1. Now, this is an example where it follows the mold of both difference of cubes and difference of squares. And depending on which one you use, you will in fact get different factors. So let's suppose I did this with difference of squares. Well, if I go difference of squares, it's going to be 8x to the 6th minus 1, 8x to the 6th plus 1. Now, 15 minutes ago, you would have said, I'm done. Now that you know a new factoring strategy called sum and difference of cubes, these are both factorable. This is difference of cubes, this is sum of cubes. So I would have to factor it again. Now it would be 2x cubed minus 1, square the first, 4x to the 6th, plus 2x cubed plus 1, and then do sum of cubes on this one, 2x to the 3rd plus 1. I'm not going to have enough room there, I'll just jump over a little bit. So this would be up here. Square the first, 4x to the 6th, product with the opposite sign, square this one. None of these factor any further, I'd be done. If I took the same question and student B sitting right next to you said, oh, I did that, but I did difference of cubes first instead of squares, you will not get the same answer. Now all the important things will turn out the same, but it will look a little different. So let's see what would happen. So if I went difference of cubes, because 64 is a perfect square and a perfect cube, the cube root of 64 is 4. The cube root of x to the 12 is x to the 4 minus 1. I square the first, product with the opposite sign, square the last. This is now difference of squares. So I have to factor this as, oh, I screwed this up back here, sorry. When I took cube root of this exponent, this should have been a 2, not a 3. Same thing here, this should have been a 2. It's another one of those things where you're watching the video thinking, what the heck am I doing? Divide your exponents by 3 to get cube root. Now the reason I knew that is because I was looking at these two and I was saying my factors were going to be different. Now it's all going to be good. Difference of squares, 2x squared subtract 1, 2x squared plus 1. You've got your trinomial. So the only thing different, you have these two factors that are the same. These two end up being different. If you were to multiply those two together, you would in fact come up with that. Now there's no strategy for you to look at this and say, can I factor it into those two? Unfortunately, no, there is not. This would be a situation where, depending on which method students use, we would go with marking both of these correct. Now, just to maybe expand a little bit, next semester in calculus, we'll run into things like this. Let's suppose I had x plus 2 cubed minus 8. And I'm trying to factor this. Well, a lot of times students' instinct is to start expanding, which probably would work, but it would be a lot more work. Remember our mantra? We want to work smart, not work hard. So don't make things more difficult than they have to be. This is like having a cubed minus a perfect cube. We would look and say, hey, this is a difference of cubes. Take the cube root of anything cubed. There's the cube root of x plus 2 cubed. So that's the cube root of the first. Subtract. The cube root of 8 is 2. Now, square the first, so it would be x plus 2 squared. Multiply these two together and reverse the sign, so it's going to be plus 2 multiplied by x plus 2. And then square your last one, plus 4. This first bracket actually just simplifies down to be x. Now, depending on what we're doing, this might be fine. We might be able to just leave it like this. If we wanted to expand this out, this would be x squared plus 4x plus 4 plus 2x plus 4 plus 4. And then I'd have x squared plus 6x plus 12. Those would be the factored form of it. If you were to expand it all out, yeah, you probably could still get this as well. So I'll show you another one of those. Let's do it. Let's suppose I had 27 minus x plus 1 cubed. Well, that's going to be, so 27 is a perfect cube. Anything to a multiple of 3 exponent is a perfect cube as well. So this is a perfect cube. Take the cube root of the first minus the cube root of this whole thing, which would just be x plus 1, cube root. That's your first factor. Now, square this one. Product of these two, and the opposite sign, so 3 onto x plus 1, and then square the last one. And remember, it's always a plus sign out in front of it. 3 take away x, take away 1 would be 2 take away x. I'd have 9 plus 3x plus 3 plus x squared plus 2x plus 1. Group any like terms in that second bracket. 2 subtract x, x squared plus 5x, 9 and 3 is 12 plus 1 is 13. And there you have it. So that's factoring that out with difference of cubes rather than expanding it all out and trying to do it as some kind of a factor theorem or trinomial question. So if you can recognize that pattern, by all means, apply your sum or difference of cubes. Okay, that's all that I have for this quick little section on sum and difference of cubes. There'll be a few little practice questions in your book. There's not too many of these examples, and however, we do now expect you to add this to your arsenal of factoring strategies, sum and difference of cubes. All right, thanks for watching, and best of luck with your practice questions. Reach out if you have any questions or concerns.